For a large fan, the best starter is not automatically the most sophisticated box. The decision begins with the starting event: how much current the supply can tolerate, how quickly the fan must accelerate, how much mechanical shock is acceptable, and whether the process needs speed control after the motor reaches operating speed. A large impeller stores significant rotational energy, so the motor must provide enough accelerating torque for long enough to overcome inertia and the fan load. For a typical variable torque fan, load torque rises strongly with speed, but the real acceleration also depends on the impeller, transmission, dampers, system pressure, and motor curve. A long ramp is not automatically a gentle or successful start. Direct online starting places the motor on the line through correctly engineered switching and protection. It is electrically simple and reaches full speed quickly, but the motor can draw several times rated current while accelerating, with a corresponding torque transient. The exact current, voltage dip and acceleration time come from the motor and network study, not from one universal multiple. A soft starter uses controlled semiconductor switches to increase the applied motor voltage during the start. Reducing voltage can reduce the current step and mechanical shock, but induction motor starting torque falls rapidly as voltage is reduced. If the current limit or ramp is set too gently, a high inertia fan may accelerate too slowly, heat the motor, or fail to reach full speed. After the ramp, many soft starter systems close a bypass path so the motor runs from line frequency power with lower losses in the starter. That makes the soft starter primarily a start and stop device, not a continuous fan speed controller. The exact bypass contactor, protection, thermal model, and switching sequence must follow the selected product design. A variable frequency drive takes a different path. It rectifies the supply to a DC link and synthesizes controlled output frequency and voltage. It can coordinate motor flux and acceleration, limit the supply-side start event, and continue regulating fan speed after startup. That extra capability also adds motor compatibility, cable, cooling, harmonic, EMC, and commissioning requirements. Compare the three methods with normalized conceptual curves, not promised numbers. DOL usually produces the sharpest current step in shortest event. A soft starter shapes the voltage and current ramp but still accelerates toward line frequency. A VFD shapes frequency, voltage, and speed together. The real curves must be calculated or measured for the chosen motor, fan, network, and settings. The decisive mechanical check is accelerating torque margin across the entire speed range. Subtract fan load torque from available motor torque. The remaining margin accelerates the inertia. Too little margin lengthens the start and increases heating. Too much abrupt torque can stress couplings, belts, mounts, and duct structures. Verify allowable starts per hour and hot versus cold starting duty. The electrical study must cover source impedance, acceptable voltage dip, feeder and transformer capacity, short circuit coordination, overload behavior, phase loss, earth fault, emergency stopping, and restart logic. A VFD adds rectifier harmonics and high-frequency output considerations. A soft starter adds semiconductor thermal duty and bypass coordination. DOL still requires engineered protection and interlocks. Now ask what happens after startup. If the fan always runs at full speed and the network can accept the start, DOL or a soft starter may meet the objective with less control complexity. If the process must vary airflow or pressure, a VFD may deliver the required operating control and possible part load energy reduction. Savings depend on the system curve, duty profile, and measured input power. The real long-while AC 800 footage and three-phase motor image make the hardware scale visible: a large rotating assembly, guarded impeller, motor body, cable, and terminal box exterior. They do not prove locked rotor current, inertia, torque curve, starter rating, protection setting, or suitability for any project. Those facts remain document and test requirements. Use a release matrix. Record supply strength and allowable voltage dip, motor and fan curves, combined inertia, required acceleration, starts per hour, full speed or variable speed duty, mechanical limits, harmonic and EMC constraints, protection, bypass, alarms, and fallback state. Then select DOL, soft starter, or VFD through an engineered study. Qualified personnel must de-energize, isolate, lock and tag, discharge stored energy, and verify absence of voltage before work.